Hello, everyone, and welcome to the Builder's Workshop. My name is Nathan, otherwise known as Old Man Builds, and I have Sean here with me today. Sean, how's it going?
It's going great. I appreciate you having me on. I apologize for the brightness of my camera. I got a new laptop, got a new camera, and I have no idea what I'm doing. But I appreciate you having me on the program, and I'm looking forward to present.
Right on. Good deal, man. Let me pull up your presentation here, and we'll go ahead and
All
get
right,
started.
sounds good.
All right, Sean, I'm going to pull myself out. Go ahead and start when you're ready.
Okay, all right. I'm hoping everybody can see my screen. So my dad is a skater. He's a surfer skater, even though he's in his 70s, and he likes to paint skateboards. So I thought I'd use one of his skateboard ideas as the first picture of this presentation. But let's get right into it. So what I'm going to be doing is going over some familiar slides and videos to have a kind of different perspective on some of them. I also have some new slides and videos, and I have to give credit to Nathan because he had me look into or re-zooming into a different perspective. So as you can see here in this photo, is that I have the sphere coil, I have the bowl shaped or the concave shaped copper pipe, which is the primary coil. But you'll notice under it that it has a sheet of plexiglass. And so now when I begin to apply power to this and the plasma is come out, this is the wave pattern that I have. This is the frequency and this is the voltage. So if you look over the lower left-hand corner, it's about 61 kilohertz. And then this VPP here is just volts peak to peak. And so we have 46 volts peak to peak. Now, when I switch the bottom from a plastic to an aluminum plate, and I run the same input power, you'll notice that the frequency is pretty much the same, but the volts peak to peak is increased immensely. Now this is something I did not expect. And so I'm just going to go back real quick here. We have 46 volts peak to peak with no aluminum. And now we have 114 volts peak to peak with the aluminum. Now, what this shows me is that normally when you're working with a Tesla coil, it's a high voltage coil, you don't really want a lot of metal around. But this is saying the opposite. This is saying that having the aluminum plate, you're able to actually access some power from that to increase the output, the energy, if you will, of your Tesla coil. So I thought that was worth sharing. Actually, I think this was Jarvis's idea, but we're going to see some ideas that Nathan has given me also. Now, what I'm looking for as I move toward building electrets is I'm looking for a power source that's going to give me a very, very intense electric field. So I'm pulling out some of my old coils, and if you guys remember this one, the one right there, I'm not in tune here. Let's see 1 second. So the first coil that you saw was the Gold Knight. The second coil here is, I call it the Roman candle. Now, the difference is this Roman candle has an almost inch thick of epoxy coating it, whereas the Gold Knight has about a couple millimeters of epoxy coating. And this is going to come into play, but these are some of my first coils, and I'm going to try to use them to create intense electric fields. So in order to create a bipolar Tesla coil, you can grab any one of your coils and you put a wire on each side of it. Here you can see I've soldered 2 wires, great camera angle there. And there you go. And you're just going to put now coil 1 in the middle. And so I'm doing the same for each of these. And then I'm going to now use the coil 1 to get them to be bipolar Tesla coils. So I'm going to kind of show you the steps here because I don't feel like it's obvious sometimes. It wasn't for me. And so now I'm going to turn it on its side. And instead of connecting one side to ground and the other side to point in the air to push off a lot of sparks, this is going to be hooked up where the top of coil 2 and the bottom of coil 2 have wires, and they're going to spark between them. And so here I'm setting it up, and it's not really difficult. If you can get your Tesla coil going, then turn it on its side, put the primary coil in the middle, and you have a bipolar. It's not much harder than that. And so now I'm going to hook up the bottom of the coil and the top of the coil. I'm going to use the alligator clips as plasma discharges. And so we're ready to go. Let's see. I'm just now connecting the ground. Okay, so there's two ways to do this. The one way is you pull one wire from one side of the secondary coil and another wire off the secondary coil, and it'll work. It'll push plasma between the two alligator clips. But what I'm doing here is I'm also adding a ground to one side. And the reason for that is it gives basically, it works as a pump, and it pumps in electrons from the earth. And so you'll get a more of an output. I hope you can see this in a little bit later. There you can see that they're going to basically throw sparks between them. I've got it grounded. I had to change out the capacitors. There's my new version 2 ZVS that we'll get into here in a little bit as well. And so there's my version 1 on top of the power supply. Just kind of showing you my setup. Here's what my lab looks like. Here's what my lab bench looks like before things get started. And with a little bit of a zoom up here, I'm going to turn on the voltage. And there you go. So this is a bipolar Tesla coil. That's it. Now, the thing about a bipolar Tesla coil is electricity is just going back and forth in the coil there. Now, because I've grounded one side of it, it's actually creating a kind of suction, and it's adding to the discharge between the alligator clips. So I'm going to space them out. My new laptop, it's acting up here. Sorry about that. All right, so we're getting more discharge. But if you can look here in this copper pipe, you'll start to see a little blue and it showing up here, and it's flickering. See that? The reason for that flicker is that when the electrons come out through the alligator clip here to meet, and the other ones come out here to meet, there's an air gap here. And so the electricity has a choice. It has a choice to either come out and hit this copper pipe, or come out here and jump the gap between these leads and arc through the air. Because these leads are too far apart for my bipolar, if I really worked on this bipolar, I would make the coil, the copper coil here, bigger, larger, so it wouldn't have this internal arcing. And so I just wanted to kind of show you what happens when you make the distance too far for the discharge. And so now I'm setting things up and looking at the waveforms. The waveforms on a bipolar, they're very different than what you would see on the standard Tesla coils that I hook up to the ZBS. And what you're seeing here really is only the ring signal. You're not really getting that other resonant frequency signal that's coming from coil 1. This is all coil 2 from what I can tell. Coil 1 doesn't show up. And here I'm going to just try to get this bipolar coil tested. Keep track of, try to figure out what it's doing. Is this the same video? I think it is. Sorry about that. Here we go. Turn down the light a little bit. It has that yellow hue. I haven't really figured out why it has that. When I take off the ground wire, it seems that yellow hue is not there. It's a lot less. So there's something about coming out of the ground that gives it that extra hue. And here I'm, my slides might be a little out of order. I apologize. So again, I'm just testing. I want to create a dense electric field for my electrodes, and this is sort of the start of that. Again, now, so here you can actually see the coil 1, and it's got those kind of strange points coming off it, and then the horn shaped in the middle there, that's coil 2. And all I'm doing is moving around these clips to different distances. That's all I'm doing. So it's interesting how the oscilloscope will pick all these different layers. So there's basically more waveforms coming out of this simple little spark gap here. Here I am again. And I'm just barely touching the distance, or I'm adjusting the setup, shortening the leads. I'm just trying to tune this thing in. So I kind of go a little bit long and crazy. My health has been a bit poor, so I haven't had a lot of chances to polish these slides. But we're going to get all angles and views of this bipolar Tesla coil. Now you'll see there that there's some plasma going on under the rubber alligator clip here. And so again, what's happening is instead of jumping that air gap, it's now pulling electrons from the alligator that's connected to, see the blocks of metal with the holes in them? It would rather pull electrons from these metal blocks than jump the air. And so that's why you're seeing the blue sort of haze here under the clip, as you can see as I zoom in here. So high voltage is a funny thing. It often doesn't take the path of least resistance. It just sort of looks for things. It looks for something, and evidently it found electrons in these metal boxes, or these metal bricks looking things, and versus going through the air. And we're going to see a little bit more of this unpredictable paths of electricity, high voltage electricity. So here I'm just kind of zooming in on the waves. So you hear the long waves here. Those are the primary, the coil 1. And then the fuzz here is the coil 2. And I'm basically trying to show them in a better way. And all I'm doing, I'm going to show you a little bit later how I adjust to get these waveforms. But I thought it's important to see them. So I'm watching one of my YouTube channels, and I'm now going to turn on some power here. That means I've got the oscillations, and now I'm going to add some AC. The thing about a bipolar coil is it does not take a lot of input voltage. This is about, it showed 7 volts, but it's actually 3. Now I hit the auto button here because my screen just looks ridiculous. And then after the auto button, it gives me something more I can manage. And now I'm just playing with the vertical and the horizontal. See here if I can pause this. I'm playing around with the vertical and horizontal measurements, the dials. And one thing you'll notice here, because it's a bipolar, that the frequency kind of comes in here, and then in the center here, it gets pinched, and then it goes out again bigger. And it's almost like this wave pattern looks like the bipolar Tesla coil output leads. So this is like one alligator clip, and then here's the voltage jumping the air gap, and this is another alligator clip. Now I know it seems probably a reach and maybe a little bit too much imagination, but I just kind of got that sense from this look, and you can see it even better here where it's pinched in the middle. Now that you look for it, see that in the middle, it looks like a bow tie. And so here I'm just again adjusting the vertical, horizontal, and trying to just get some patterns, if you will. So what I'm doing here now is I'm moving to creating two plates where I can get a super intense electric field between the plates. And so I'm using the bipolar Tesla coil setup to put a high voltage potential on these two aluminum heat sinks. And right now they're too close because the electricity is traveling between them. But if you pull them apart a little bit, you'll hear them crackle, but there'll be no discharge. And that's when you have a really intense electric field between these two copper plates. So let's see here. Just kind of showing you how it comes apart. So I'm doing the one-handed filming. I know you guys have probably done this before, but I'm just kind of showing you how easy it is. It's just the Tesla coil coated by a lot of epoxy. I don't recommend this because it doesn't help a lot. It helps a little, but it was learning. So I keep showing this, and the reason for it, on the ZVS board, when you power it up on the DC side, when it's oscillating, it always should be in milliamps. The input is 12 volts. It should stay 12 volts. The input current should always be a millivolts. That's always a thing. And that's why I sort of emphasize this in my presentations, because ZVS is finicky. And if you don't understand that part, it can drive you crazy. Now I'm going to add the AC, and we're going to see. So if you see it going wacky like that, see if I can grab it. No, I can't grab the slider. It's because I'll show you here in a second. You'll see it. This is such a crazy magnetic electric field that it causes the displays on my Variac to go crazy. And look at it, it's about 3 feet away. And this thing just puts out the energy. And it's kind of cool too because it's on the heat sinks. And so the heat sinks aren't going to get hot. They dissipate the heat quite quickly. So you don't have any really hot spark gaps, which is something that can occur. Usually spark gaps get hot and you have to figure out some way to cool them. So having a spark gap made out of two heat sinks, you're sort of killing two birds with one stone. And as you can see again, the wave patterns are just wild. Here you can see when I take it past 7 volts, 8 volts, you get to see it from this good angle in the dark. You'll see that instead of the electricity coming out, it's just going to leave this inch thick of epoxy to touch the copper tubing on the outside. So it's a balancing act. You kind of have to, and you can see this wire here on the right. It's trying to give you a streamer to supply into this coil, but right now, because the copper coil wrapped around the top here is robbing it, it's not able to connect. This is one of those patterns that I really like. This seems to be unique to what I'm doing with creating the electric fields. It's so telling. You can get a reading on, it's 500 and roughly 40 something hertz. And the volts peak to peak is interesting. This is all coming from those two plates. So, oh no, wait a minute. Oh boy, slides out of order. So what I'm doing is I'm incorporating some of the coil slides that I shared last time. And so I'm sorry, I have to go back here. Let's see if I can do this. I was wrong. What this one seems to look like is a cone. So if you remember, you had that sort of bow tie type pattern when I had the bipolar Tesla. where the alligator leads were sort of had a discharge point between them. But when I hook up the cone coil, I get a shape that's representatory of the physical geometry of the cone. And that's why I had this video here. So I don't know why I'm zooming in here. Oh, to see the frequency and the voltage. So this is a couple hundred volts peak to peak that's being emitted in the air from about 6 inches away from this cone coil. So that's a decent voltage. 6 inches away, you're getting about 200 volts. It's not bad. Now this is the standard, if you will, waveform of the ZVS that you're familiar with, where it's a standard Tesla coil. And so this one seems again to be close to the geometric shape for the standard coil. Now, what I was doing here is I was using the spool of copper wire as a ground, and I was able to really get huge discharge from this little 3-inch coil here. And it's using just connected, instead of the earth ground, it's connected to that spool. It's about a 10-pound spool of about 23 gauge copper wire, magnet wire. So this is one of those problems where when your coil 1 is too close to coil 2, it's not going to discharge from the top. It's just going to say, heck, I don't want to go out in the air. I'm just going to slip out of the epoxy here and light up this copper piping here. So when you're building these Tesla coils, it's always a balance. It's always a balance of pressure, voltage pressure. So these are one of my weird diagrams. So on the top here, what you're seeing is the ZVS circuit powers up this Tesla coil, and the Tesla coil is connected to ground. So it's receiving basically energy from the ground, if you will, and that energy then is coming out the discharge point. You'll see those big purple lightning bolts. Now, what I'm trying to do is to polarize a plate. I want a plate to be either positive or negative. So if you look below here, you'll see that I put a diode here connected between ground, and forgive me if the diode's not correct. I'm super dyslexic, so I have the tendency to just put the diode in, and then if it doesn't work, I switch it because it's easier for me. But what I want to do is I want to say, hey, you know what? I want to keep positives out. I just want the negatives. I want the electrons coming in. I don't want any protons. And so that's the idea here. So I'm going to put this idea now to test. Here I have this super high voltage diode, and I'm going to connect it to earth ground. And now I'm going to say, okay, let's see if I can just get only one polarity, either only protons or only electrons, and watch that. So what is going on here? It's not burning up the diode. That's not what's happening. What's happening is the electricity is jumping over the diode. It cracked me up when I saw this, because I thought, okay, this is a 25,000 volt diode. Let's see. Sorry, I should move out of the way here. Okay. If you could see it, and I'll probably have some better video of it, but it's just literally jumping over to the other side. It's ignoring the diode. It's saying, I have too much voltage for you. Get out of my way. I laugh because it's funny how you'll have a plan in your head, and then the results are completely not what you expected. There you go. Can you kind of see it shooting over? It's just saying, you know what? I don't want to go through you. I'm going to go over you. So yeah, this is my attempt, first attempt. I'm going to try it the other way. No, it's hilarious to me. Yeah, just kind of go right over it. All right, so as I'm getting into creating electrodes, I'm studying how electric fields work in certain geometries. So right now we're seeing a rod of protons and how the electric field would look. And so when I'm building an electrode, I just want to get an idea of what are the fields going to do based on the geometry. And so I know Jarvis, I call him Jar Jar, he's mentioned that a rod might be the easiest electric geometry to create. And so I thought I would do a little bit of visual research on that. Now, when you saw those two aluminum plates, I found this physics site where it actually showed you what the field looks like in between the plates. And so when the field is exactly straight up and down between the plates, that's when the field is the strongest. And so if I'm going to be building electrodes, I want to kind of have this kind of field between the plates. So the top is red, which is protons, the bottom are electrons. And so that's, and this is a capacitor, if you will. And the only difference between an electret and a capacitor really is that the capacitor leaks and it's going to lose its charge, but electret is not supposed to. Just like in a permanent magnet only loses 10% of its magnetic field every 100 years. That's why we call them permanent magnets. An electret is going to be the electric field side of that. Again, I'm just kind of digging in here into what the fields look like. And so now these are going to be my two plates. These are going to be what I'm going to be running the current through. And yeah, my slide's a little out of order. I apologize. But I think you guys understand what I'm doing. And so here I'm just kind of showing my setup. I want to put these two plates. I'm expecting those intense magnetic field, or I'm sorry, electric field lines. And so here I'm getting a real strong voltage. The voltage is so strong. This is a bipolar, by the way. The voltage is so strong that it's the one that jumps over the diodes. So this is a pretty powerful field. Now, granted again, I should not have it arcing and sparking when I'm creating the electrodes, but I'm basically just testing my theories. And so away from the flat part of the plate, the waves start to bend. And so that's another interesting phenomenon. Let's see here. So this is from my notes. So the thing about creating a strong electric field is you need four things basically. The larger the plates, the better. You want a good dielectric, and then the distance of the plates, as well as the voltage between the plates. And so these are the four things that I'm going to be considering as I start setting up a lab of powerful electric fields to create electrodes. Now, this is one of my favorite slides because this is something that I don't think is very intuitive. And so what you're seeing here, we'll start on the upper left here. We have a hollow sphere in gray. Now, if you make a hollow sphere over to the left of, let's say, copper, but it's hollow, then what's going to happen is the charge is going to be only on the skin, okay? It's going to only be on the skin of this sphere. If you go to a non-conducting, so instead of copper, let's say this is made out of glass, it's non-conducting. When you try to charge it, you're still going to only have the charge on the skin of the hollow sphere. If you have a solid over here to the right, solid conducting, let's say this is copper. Even though you could put a lot of charge in this copper sphere, it's only going to be on the surface. You're never going to penetrate inside that copper sphere. But if you have, let's say, call it glass again, if you have a glass ball and you put voltage on it, it pushes charge all through the entire thing. That's totally unexpected. You see, we use copper wires for a reason. because copper conducts electricity really well. It handles charge really well, but not when you have this geometry here of let's say an insulator, glass or ceramic, or just pick anything that doesn't conduct electricity. That thing, if you run a voltage on it, it's going to be from the center all the way out. It's going to align and affect all of those atoms or molecules. And that I thought was one of the strangest, unexpected things that I discovered in my research of electric fields. Because when I create an electret, it's going to be of a non-conducting material. It's going to be, let's say, epoxy or glass or mica. And those things aren't conductors, those are insulators. And what I was worried about is if I put a charge through those insulators, it would be only on the surface. And only like something like aluminum or copper you could penetrate down because they conduct electricity. No, it's the opposite. So this really encouraged me, this finding, and I thought I would share it with you guys because my guess is that it wasn't intuitive to the audience. Okay, so I took apart an old speaker from the thrift store, and what I'm doing is I'm trying to screen out the sand, as it's going to be one of the materials, silica materials, that I'm going to be using as the materials for the electrets, the insulator through the electrets. So when I find a binder for this sand, and I'm going to put it under high voltage, it's going to penetrate through the whole thing. And the goal is to hold that charge inside. And so here I'm just kind of doing the manual tasks. Here, I shared this last week. So if you missed it, this will be new to you. But this is the glass powder that I ordered. This is the glass that they use when they paint streets. So if you have that center white line, that dotted line, and at night it sort of glows under your headlights, this is the powder glass. So it's a rounded glass. It's not jagged or cut you, or it's not dangerous. It's all very soft to feel. And so I wanted that because there were too many problems using broken glass. And so I'm running electricity through them, kind of seeing if I can create different fields. So what you were seeing in that arcing and sparking is you're actually seeing that it was running through the glass as the glass being a conductor. So the voltage is pretty high because glass is a huge insulator. Here again, just kind of moving around, testing high voltage in the elements that I'm going to be using in building these electrets. And I do readings. If I run a charge through the glass, it didn't really do anything noticeably. So that's good to know. That's a failed attempt right there. And so here I'm going to start the oscillations. And no, I'm sorry, this is just another high voltage power supply I bought off AliExpress. And I'm just taking the negative end here and seeing if I can align and charge all of these glass particles. And I was able to. So you can see it's 8,000 volts, 9,000 volts. It's upside down. I apologize, but that's how the meter works. So yeah, it did work. This is a route. This is something that's promising. Let's see, so here again, having troubles. I'm basically doing the same thing here. Here I'm going to read it. I think this is a different power supply. And here it didn't really impress me. Not really getting anything exciting here. It wasn't, it's 3,000 volts. I guess it was something, but it's not the higher voltages that I was getting on the previous method or previous power supply. Sorry about that. So here I just have a piece of copper coil that I made. I'm hooking it to ground. So this is grounding out all the glass after I put all that charge in it. And so I'm hoping to now measure it to see that it's all at equilibrium. And this is just helping me understand how I can get insulative materials to hold electric charge. And so let's see, after grounding it, there's still a couple hundred volts in there, but the grounding of the glass did work as expected. I'm always using my Klein Tools Pro Thermal Imager for all of my experiments to see what's getting hot and what's not, and just making sure things are efficient. So I was trying to put 2 electrodes in water, and these are Teflon shavings. I was testing this with nylon. I was trying to figure out how these incredibly positively charged materials would react if I put 2 electrodes in water. What I was hoping for is that I could get a kind of alignment to show how the electric field looks. And I didn't. All I got was this sort of ionic wind that was pushing around the water. So that was a failure. Here I cut out 2 copper spheres, and you see me touching it. There's a huge, massive electric voltage between the 2. So you can see that there's a strong electric field because look at the discharge there. So what I'm going to do now is put a liquid insulator in there, a little epoxy, and I'm going to see if this 20-something thousand volts can polarize, if you will, the epoxy, and then hold that polarization and become a little electrode, if you will. So there's the 2-part epoxy. I'm going to put it on this insulator here. And the reason is I don't want the copper arcing. So the field will still be able to go through this just fine. But my hope is that it'll align the epoxy molecules, and then that high voltage will hold inside that dried epoxy. So there it is. Arcs and sparks are bad. So I had to always adjust this throughout the drying of the epoxy, and you can see the mess. So again, I'm just being quick, and this is a stream of consciousness. This is not reading about it. This is sort of just getting exposed to the environment, getting my hands covered in super glue and whatever materials I'm working with. And so this is the experimentation I'm doing. So this is a slide out of order, but there's a program called oh, I forgot the name now. It'll come to me. Java TC. There you go. Where you can put in parameters, and then it'll tell you how many windings you'll need for a certain frequency. And so Nathan wanted 1 megahertz, so I keyed in the values. He's getting about 1.029 megahertz, which is not bad, or 1029 kilohertz, and he's getting it across the primary and the secondary, so he's golden. Now he has to just follow these specs. So he needs a certain 10 inches of windings, if you will, and so on. You can get the specs from that. So I read your guys' comments. I read your guys' stuff in the chat. I take notes. Here's Delta something B. He was kind enough to share this a few days ago. And so I just want you guys to know I really appreciate you guys reaching out to me. I love the feedback. Keep it coming. I do care about what you guys are sharing, and it's only health and limited schedule that prevent me from getting to you guys in a quick manner. But just let me know that I just want to let you guys know that it really makes me happy that we have this back and forth and we're sharing ideas. Now, I'm getting to some slides and videos where Nathan challenged me and said, you know what, how can you really get more out of the earth? And can you really have a similar reaction to lightning on the earth? And so what you're seeing here is those coils at the start here were laid up on the ground wire, and they were lighting up by the ground wire. So there was energy over on the ground wire. Now you can see I'm putting it on the balls here, but these are also connected to earth. the copper spheres, not balls. Terrible. So this kind of exhibits that there's all this energy in the ground. Here's another sort of way you can see it. You can see that over on the left, it's just discharging out to the air, but it's creating some kind of suction, and it's just pulling out from the right electrons into this sort of main plasma discharge point. Now, because it has a frequency, there's a back and forth of it, but it's still fascinating to me that you can see this sort of over here on the left creates a suction and just pulls electrons right out of it. And notice here that it's pulling it from that spool. And we got that real interesting waveform. Again, I like to just look at the waveforms for all the different ways that I'm connecting high voltage. Here's another one. I was sharing these with Nathan, and he used these as part of the thumbnail for the video, and it's just so cool. So what's happening here is I just turn up the voltage a little bit, and what's interesting is there's so much pressure in this sphere, it's pushing plasma out the top, but in the wire spool, it's being pulled out. The energy is being pulled out from the wire spool, and instead of it getting just pulled right into the top copper wire, it goes right through the epoxy. This is the strange effects of high voltage. You cannot get electricity to run, regular electricity to run through epoxy like that. But yet, electricity doesn't take the shortest route. That's one of the things that Nathan sent me a video on, how electricity doesn't follow the same route. And you can see that right here. The most efficient route, sorry. The most efficient route would be straight shot. But you see, it doesn't know that this copper wire is here. So it's just being pulled out. And then it sees here the epoxy and says, hey, I'm going to grab for it. And then it's coming out of the spool here, and I'm using that as a ground. Now, Nathan brought up the good point. I'm going to replay it here again. Nathan brought up the good point where he thinks the spool of wire that I'm using for ground is acting like another Tesla coil, and it's a good point. And so he recommended that I move the spool of wire further. And so what you're going to see here is I'm going to put this spool of wire, I'm going to move it. But I just wanted to show you here real quick. Okay, so you can see here on the right, this spool of 10 pounds of copper is providing a huge source to where the top discharge here of the sphere can just create a kind of suction, if you will, and bring these electrons or these protons out. I know that's not the exact way to say it, but I'm using language to some degree that's accurate. But this is all new to me. I'm getting kind of a close-up here, and it just cracks me up how it just dances on the epoxy instead of going to the wire, the simple wire that's right next to it. Again, some more of this. And by the way, too, I can't go over 10 volts, and I'm working in the 3 to 4 volts to show you how efficient resonant frequency is. And when you're dealing with a source of electrons or protons like this spool of wire, and you can see even down the wire, it's just drawing energy out at the different points here, and very fascinating. I don't know if I click next here. Sorry about that. Let's see. Okay, so I'm putting on top because I get asked sometimes, hey, can you put the ground wire on top? And it gave a very interesting, a very different waveform, which was, I thought, worth sharing. I don't know really what it means, but I thought it was in this position, how it changed the waveform. So I'm moving the distance from the top, and you can kind of see the spray. Again, this is the copper wire from the spool. So that spool has a lot of density in its energy. It's kind of nice. I don't need a ground. I can use this, and we talked about using the copper spheres Well, here we are using a spool of copper wire. And it looks like, if you look over here at the tip of the wire, it looks like you've turned on the water and it's just spraying out of the sink. And so I thought that's kind of fascinating. Also, too, I dial it up to a few more volts, and this sphere just pushes out the plasma. Oh, so I broke off the wire off the sphere, and I couldn't find it. And I didn't want to dig too deep, so I thought, you know what? I'm just going to put some juice into it and see where the wire broke out. Put about 20 volts in. It's going to show more here, but the dial is wrong, way wrong. So I'm going to dial it in. Look at that. Oh my goodness, there's so much energy. And it's what's happened to this output. It's very different than when I had the little antenna sticking out, if you will. And so I thought this was just fascinating. It did also help me locate the wire because it's sort of charred around the part that where it broke off. So I was able to dig it out. But whenever I'm working with my coils like this, if you just turn it up a little bit, you have amazing voltages that are plasma discharges. So now Nathan said, hey, you know what, move that spool away and see if you get the same effect. So I'm going to put the stool over here in my messy corner. And that way it's far enough to where, is it really acting like a ground, or is it acting like another secondary coil to Tesla coil? And so I was setting that up as per suggestion. And so here you see we're ready to go. And now we're going to see if it has the sort of same behaviors as before. And I'm having a little fun with the camera. Let's see. Do I turn it on? Slides are out of order. Thank you guys for your patience. We'll get back to that. I wanted to show you this because, again, this slipped by me in the last presentation. But now what's providing a source of electrons is the upside down cone here on the right. And look, it has the same yellow hue too as the ground. And so it's interesting that really any source of electrons, whether it be a spool of wire, whether it be one of these wound epoxy coils, or their copper spheres, they all can be sources of ground. Now, I ordered some spheres filled with different gases, and I didn't clean the lens of because I use my iPhone for these videos, and so it's real hazy. But this is supposed to be argon, and I'm going to write them because they made a mistake. They mixed argon with oxygen, and so I thought I'd share because the oxygen is the green, and the argon is this bluish purple. I thought that was interesting. And what I'm going to be doing is I'm going to design a Tesla coil that causes geometric shapes to be put in these different vacuum spheres. These weren't cheap and they're fragile, so we'll see how they turn out. Here we go. I just kind of put it on the copper pipe here, and I'm putting about 2 volts in. And again, you're seeing the green oxygen inside. And I hope to do a lot with these, but I thought I'd just kind of introduce them. One thing that's really interesting too is that it's creating a conductive tunnel here, and it goes to argon to green oxygen to argon again. And I think that's interesting how they're not mixing. Argon's an inert gas, so it's not going to mix. And so to give you an idea, if I just turn it up a little bit, how much power is in this sphere, a couple volts, and it lights up those gas tubes is pretty incredible. Here again, I'm trying to, and what I've been able to do right here is hard to see, is there's actually a sphere of oxygen now in the middle. I'm going to get this to be a little bit more clear, but I thought this was pretty interesting. Here's what they look like. I'm taping it on this flute that I got from Las Vegas with my wife. And so this is what I'm doing is I'm taking these different gas balls and putting them close to the sphere. So again, placing it near and seeing the same kind of reactions. I'll get better footage later. And let's see if oh, so I do it in the dark. So we can kind of see it's pulling the electrons from the spool of wire and what it looks like. It's pretty interesting. I'm keeping the voltage really low so we can get some different effects. This is what it looks like with light, I mean. I turned it off here. This is the better angle, if you will. And you can kind of see a lot more plasma coming out in the dark. You can kind of see there's this fuzzy haze. And that haze is not bad. It's when it discharges as far as creating electrets. You don't want any flow, but this sort of powerful ionized field is pretty close to what you want to make these electrets. Here I'm turning the voltage up a little bit, and man, look at that thing. It's going right into the epoxy. Doesn't want the copper or nothing, just right in there. All right. I gotta stop starting my videos with the oscilloscope. It's hard to predict what I'm going to talk about. Sorry about that. So I'm going to be showing you how to adjust the oscilloscope for different fields, and that's coming here in a minute. But what you're seeing here is that I play with the vertical, and then I play with the horizontal, and that's all I do. I don't do anything fancy, and I just do it until I get certain shapes or that I'm looking for, and they don't come out looking nice right from the bat. But this looks familiar right here, see? And so I adjusted the vertical and the horizontal, and you can see now I'm getting the primary and secondary frequencies in the Tesla coil. And I darkened the room a little bit, and I'm just barely a volt and a half. And I kind of wanted to share how you can see streamers coming from the bottom and streamers from the top. And there's a lightning video that maybe Nathan can show after my presentation that does this similar effect. And here we have it again. And you can see that the little streamers coming out, and so lightning doesn't, from our clouds, doesn't come straight down to the earth. What it does is it does this. It sort of creates energy on top, energy on the bottom, and it just starts. See how it's starting to come up from the bottom? Bam, that's lightning. It's trying, boom. So I was trying to emulate that lightning video where the lightning starts coming up from earth, from ground, from dirt. And then it comes down from the clouds, and then when they get close, boom, you get a lightning strike. And so this was inspired by Nathan. I appreciate that, good idea. But this was the closest I could get to that phenomenon. I think we're almost done here because I'm talking a lot. Let me just skip through some important stuff here. Whenever I see the rod down the center of a Tesla coil in Nikolai Tesla's patents, I always think of Nathan. Nathan and Tesla are the only two people I know that have done it. So thought I'd share that, kind of random. So if I show you, let's see here. This was something that should have been in a better order. But when you have the electricity, the resonant frequency coming up through coil 2, it starts to get more and more dense until you get a discharge. And this is the description of this Tesla coil. So if a slightly cone shaped with a rod down the center is explained by one physicist that it does this. It sort of moves and then it gets pinched as it gets to the top. And that makes sense. All right, I'm going to skip here through a few more because, guys, you've been great listening to me blather on. This was just a piece of glass I bought at the thrift store. I thought I'd put some plasma through it. As the glass was heating up, it started having these really strange mirror type properties. And so I thought it was fascinating. It did get hot. Running it for 30 seconds, it was 112 degrees. So just playing around there. Let's see. This is a Tesla coil that I'm working on, where I'm replacing the MOSFET or the transistor with a relay. So I'm hoping to get this thing working. And so I thought I'd share it, so to be continued for next week. This is something that blew my mind. This came from Ian. He wrapped a cone and a cylinder with the exact same number of turns of wire, the exact length of wire. They each have 33 ohms of resistance, which just means they're totally dialed in. But when you look at L here, and you see that on the cone side, it's 409 millihenries. And then you look at the cylinder side, L is 284 millihenries. That blew my mind. What you're saying is this design, this shape here has double the energy of this shape on the right, all because of the cone. The conical has maybe some sort of point where it pinches and it increases the millihenries. Henries are basically how much magnetic energy you could store. So this cone can store almost double the magnetic energy than this cylinder, yet they have the same amount of copper. Absolutely amazing. Let's see here. Let's see. Sorry, guys. I'm going to get to the end here. I think what I'm going to do is I have a whole bunch more to talk about. I'm going to save that for next week. I'm just going to try to get to the end here. Actually, I don't need to do that. I can just do this. Let's see. Stop. Oh, not that. Nathan, are you there?
What you doing, Sean? Playing with the buttons?
Yeah, sorry for my video here. Again, I look like I'm on the surface of the sun. I cannot fix my camera, and my room's dark, so I apologize for this, but my health has been on a winning streak. I wanted to get a face behind the voice, so I want to thank you guys in the chat for listening to me. I appreciate it, and I guess I'll start with you, Nathan. Thoughts?
Well, hold on. Let's give you a big round of applause. That was an awesome presentation, Sean.
I appreciate that. Thank you so much. It means a lot. I appreciate that. It's this is the high point of my week or my month, and I really couldn't be this happy without you guys, and especially Nathan creating this safe space, if you will, for us fringe scientists who aren't afraid to say something wrong or say something right, but to follow the data, follow the experiments. Don't listen to the negativity. Don't put yourself in a box. Live outside the box, I think, would be a good description of my friend Nathan here.
Yeah, not quite normal, huh?
No, with you in your underwear at midnight in the pond with all those 4-foot.
Well, hold on. It wasn't in my underwear. Let's clarify that. That just sounds wrong. You may have seen my underwear. I had pants on.
It was plumber butt. Okay, that's what we had.
There you go. Oh,
that's awesome.
I even put a sensor on it. Come on.
Nice. All right. Well, so Nathan, sorry I interrupted you. Thoughts?
Dude, sorry, I was putting up the chat. Dude, that arcing between the ground and the wire, or excuse me, the coil and the wire, how it looks like lightning. The fact that it stops for a while and then builds up a high voltage in there and then shoots it off, that part was amazing. Because it's like so thick and big, it's just boom, right down. You know what I mean?
Exactly. And that's what you said in your message. And I thought, well, wait a minute. And you had sent me that video of actual lightning and these little lightning hands come creeping up from the ground, and then they meet in the middle. And I thought, oh my goodness, I have to try that. So I set it up and it worked.
Yeah, it kind of tells you a little bit about the Earth, doesn't it? There's an energy field below our feet we don't really realize is there.
Right. Yeah, exactly. Here I provide this coil of this long coil, 10 pounds of copper, and you'd expect electricity to come from it because it's copper. But to see it come from dirt clods. I think that was one of your experiments where you were pulling energy from a dirt clod. I think that that's my next test, using some of the things I'm using.
But it's just energy and capacitance. That's all the ground, really is. And you don't
Yeah,
recognize it because it's not hot energy that's coming out of there. It's the
right.
opposite side. So when you did your experiment, you notice your tendrils every time you get those nice, beautiful purple tendrils that come off of those things.
Mm-hmm.
You notice that the field's different. It it doesn't behave the same way as your say sword shaped Tesla coil voltage that comes out
Mm-hmm.
when you use your variac and stuff. It's a lot different.
Right.
So you're actually flipping that field. So you're creating a draw. So it pulls the energy out of the ground and brings it to it. So
Yeah.
it's a field flip. And uh,
Yeah.
it's hard to really understand it until you see the videos like what you're doing and you start pulling that energy out.
Yeah.
I mean, now think about it this way. You moved your big coil of wire away from it. So you got away from the primary being a
Mm-hmm.
possible source of turning it on, right?
Right.
So now think about it like this. Where's the energy come from? So
Yeah.
it's not coming out of the ground. It's not coming from the primary in your Tesla coil. It is
Right.
literally pulling the energy out of the air.
It's fascinating. It's just using its surrounding environment.
Yes.
It's way more than you think. It's not a copper wire with electricity as we sort of think about it, and it stays in our walls on our copper wires. It's this more of something that lives and breathes around us. I know it's not living, but it's kind of a good analogy.
Well, think about it this way. It doesn't do it with the traditional Tesla coil. It has to be that Tesla coil has some sort of field flip in it. That's the key right there.
Yeah,
So
right.
I do it on a much lower level than what your coils are by all means. But that rod down the center, it creates that environment for that ground to pull into it. Yours is more magnified because, all the windings and stuff you got on there.
Yeah,
So that's what I think is totally fascinating. It is
right.
literally put a capacitor in between it and pull the energy out as it comes in.
Hmm.
So you could just pull energy from the ground all day. As long as that pumps right and you don't have any spark over, pull that energy from the ground all day.
Right. And to think about, the input was 2 to 3 volts. It's the power resonance in it, and it does seem to have the extra energy qualities that you're describing. Um, yeah. So I had a question for you.
Wait until you can get a Tesla coil to pump down in the regular hertz and not the kilohertz or
Yeah,
megahertz where you get your coils. It literally will change the game on the amount of energy you get.
it's it's been something on my list. I'm calling it the low frequency Tesla coil. I have sort of this bin of ideas, and I see it, and then I get sidetracked. One of the things that made me go back to filming or recording these same coils that I've shared with you guys was you in putting it in my head. No, there's something else happening here, and so that was the impetus for me getting excited about tonight. But I do have on my list a low voltage Tesla coil. How low can I get it? And so that's going to be a fun journey, um, because once you get to a certain frequency, below a certain frequency, it gets harder and harder,
Mm-hmm.
a lot harder. I mean, if you think about it, the lower the frequency is, you're going to have, if I'm doing the math in my head, you're going to need a really large inductor or a really large coil or a super, super, super dense coil. and a super large capacitance. I mean, it's just going to be interesting.
So the turn is, the lower the frequency, the higher the amperage field. So when you pull that energy out of the ground, we're pulling it out in voltage right now.
Mhm.
But wait until you start lowering the frequency. The more amperage you're going to pull out of that, you're going to just overload a bunch of caps on your journey to get there.
Yeah. No, I can't wait. It's awesome.
That's why Tesla used those caps like you showed in that thing. You had them back to back, but when you had them like this,
Yeah.
that's why he used them that way, because he's pulling amps out of the ground too.
Yeah, and Tesla writes about ground as in the terms that you're using. My question came to me now. Uh, have you noticed that his coil with the rod down the center has a slight, almost a conical shape, if you will, a cone shaped? Have you thought about bringing in your coils, your secondary coil with all your windings to maybe to a sort of slightly conical shape as he does with the rod down the center? Have you thought about that?
I thought about it because Tesla's. He always said there was more power in those cone coils than there was anywhere else, and you showed that today.
Yeah.
But yeah, you're right. That is something I need to look at as well.
Yeah, it just dawned on me today. Yeah. All right. Well, I'm looking through the comments unless you had more to share, Nathan.
Well, I think that what you did with that round Tesla coil is absolutely revolutionized the way Tesla coils actually work. And
Appreciate that. Wow. Yeah.
you have so much more going on there, Sean. I've been avoiding building one. I do not in any way want to steal your thunder on that. You know what I mean?
Oh, I mean, yeah, but it'd be your own flavor, and I'd learn a lot from you. I mean, I appreciate your sentiment.
Yeah, I'd rather tell you what the experiment is and have you do it than to do it myself. I hope you understand that. It,
Okay, I know, I
it
appreciate it.
you deserve all the credit for it, is what I'm trying to say.
Oh, thank you. I appreciate it. I've learned so much from you and the guys in the chat. So this is I guess you can say a team effort.
Yeah. Oh, it
Thank
is.
you so much, Nathan.
So don't even worry about it. This is what science was meant to be. You come in,
Yeah,
you share what you got, everybody gets a look at it, and then we can all determine on our own what's going on. You know what I mean?
yeah,
And then
exactly.
the inventor comes out and says, "Hey, this is what I see. This is how I see it working." And
Right,
then you go, "Okay, what was my assumption of it? Does it match what he's seeing?" Because the inventor knows all when they build something. They literally can see
right,
every interaction that's going on, where you're kind of a step away from it, you know, when you look at it through the camera. But when you're in the room, you can
mhm.
feel the environment. You can
Oh, yeah.
feel when it heats, when it cools
Oh,
down.
that's
Yeah.
hard to express in the videos where
Mhm.
the room is electrified and you can just touch anything. You can touch the wall and it'll zap you and you're going, wait, where did that come from? Why? And then there's this I guess like you said, you have to be in the room to see it and you can't capture it on video. Um, in video, you're only seeing maybe 75% of what you're experiencing in the room.
Yeah.
And that's a lot. I mean, it's a total lot. It cracks me up because I'm nerding out on my stuff and then I get to share it with you guys. You guys are so cool and nice to learn about it because I'll sit and dial that sphere that you saw. I'll dial it up to a foot long arcs and I'll go work on something. And it's just fun to have all that power being thrown in the atmosphere and it's like a lamp. It's so interesting that a few volts, if you can tame it, I guess, it becomes so wieldy and so, well, unwieldy, I guess. Both.
Well, think about it this way, Sean. If you think of that ground coil that you're using, right? The spool of wire,
Yeah.
and it's pulling energy out of the environment. Now, I just want you to just think about this for a second.
Okay.
Your whole understanding of energy and over unity now has to change. You have to stop and look at it for what it is. When you pull energy out of your environment, and it's not being made by the ground, it's not being made by, a coil being run next to it. You're not putting a battery source to it. You're literally pulling energy out of the air. Your whole
Right.
definition of over unity has to change.
Yeah.
You literally have changed the understanding of the Tesla coil by doing it. Like, people always want to talk about 0 point. Where does it come from? Well, this fundamental understanding has to be understood before you get there. You have to pull the environment into what you're working on.
Yeah.
And as soon as you learn that hey,
Mhm.
it's not just the Tesla coil is a pump. You're using it as a suction device in order to pull the energy right out of the environment.
Yeah.
That's the point of 0 point energy. So that's why I want you to get all the credit on this, Sean, because you're in a different level than anybody
Appreciate
making a
that.
sparkler.
Appreciate that. It means a lot. It's just sort of the opposite since I've been in this part of this group, and I think we've been now together for a year. I'm going to check my oldest video, but that's kind of the theme is when you learn conventional electrical engineering, you basically learn to shut out certain things in order to do certain things, and those certain things you're shutting out, we're embracing. Those things that they're trying to drive out of the circuit, we're saying, no, 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 no. Let's just sort of guide these things to our own purposes. And I think that's the kind of theme. Correct me if I'm wrong.
Yeah, pretty much.
Yeah. Do you want to look at the comments?
Yeah, actually, put them up.
Awesome. Let me see here. A lot of love, guys. Much love back. Awesome. Let's see here.
So
Hey there.
let me just mention this, and I'll just say this because I know Todd's in the room here watching.
Okay.
If you wanted to multiply the energy in something like this that you pull out of the environment in the room, you are literally going to have to pin a static field inside of a scalar field. Okay. But you have to make them in layers, one after the next, right? So when you look at T.T. Brown's disk and you see the different layers, he's putting a static field in between what would be considered a scalar field, or I call the one wire energy field. It literally stacks them, so you're multiplying the energy layers, and the outside layer works just like your Tesla coil did. It pulls the environment in the room. So just as a heads up on how that system actually works when you do it, there's a lot of building involved in order to get there, but that's the actual flow structure of what you're doing.
I'd love to go step by step of what you're talking about. So we'll have to take another call because I mean, it excites me that you're pointing out things that I haven't thought of. And I thought, okay, more arcs and sparks. No, let's look at recreating lightning, and that just blew me away. And then of course I'm finding grounds everywhere: the spool of wire, the copper spheres. So really, there's a lot around us that has energy that can be used, if you will, standing by. And I think your analogy of the Tesla coil being a pump is really good because it it basically means it's drawing out or pushing in the energy around it from these objects. Yeah, crazy cool, good stuff.
Well, wait until you create one 180 degrees out of phase, Sean. Then the pump goes both ways, and the center, here's your center, but here's your pump.
Yeah,
Just like that. And Now you can start to see it. It pulls in the one side and ejects it out the other. And then it continues to fill into the room. And then your whole room, after a while, is completely electrified. And
Wow.
yeah, you're feeling it thick on your body. Like your hair is standing up
Wow.
everywhere. It's thick on your body. You know what I mean? You've now pinched everything inside that room, and it starts to now grow and grow and grow. And it's not going to stop till you turn it off.
Right. That's exciting. I know you've shared that phenomenon as well as Gerald has.
Yeah.
I feel electrified, but I'm not that quite at that point. What did you think about the waveforms on the O-scope? Sort of matched in a way the geometry of the coil. So you had the bipolar, and it had sort of those two ends pinched in the middle. You had the cone, and it came out more conical. And then the cylinder comes out more cylindrical. What were your thoughts on that?
The cone is the best one of the examples to see it, because it literally makes a cone on your oscilloscope.
And exactly. And you haven't seen that cone on other coils. Usually it has that more teardrop, or it has that more rounded shape. So yeah, I thought that was pretty interesting, because I know you pointed out to me that that there are geometries can really have more of a multi-dimensional aspect to them. So you'll see something two-dimensional, and really there's a three or four-dimensional behind it. And you're kind of seeing that the waveforms are basically dimensions of the geometry of the coil.
It's compression.
Is that a stretch, what I'm saying?
No, you're right. But you have to look at the compression of the coil you're building. Where are you compressing it the most? Where's the most energy going to come out of it? You know what I mean?
Right.
That's one of the important points. One of the, just so you know, when we do a lot of these projects, the whole idea is to create a capacitor that can hold all of the volume coming out of a Tesla coil.
Yeah.
You see, that's the hard part, right?
Right.
Is you don't get a natural capacitor to do it. You could use some kind of crystal capacitor to do it. There's one or two, I think, out there that work. But you're looking to amplify that. So what if I just told you that we use bismuth to amplify that between two plates of aluminum?
I mean, yeah, the metallic properties of bismuth are very peculiar. It's not really a metal. It is a metal. It's not really an insulator, but it is an insulator. It's an interesting material. So you're talking about making a bismuth capacitor? As bismuth would be the dielectric?
Bismuth is the amplifier to the capacitor. It's okay. So I showed you that video earlier, and we're looking at this. I'll show it real quick.
I tore it down a little bit, and here's what I see.
Yeah.
There's layers, and that's just...
So that, just for reference, this is a DC flyback, and it's broken down. Right. And what you're actually looking at is this is the core of it. It's a simple winding, right?
Yeah.
But then the outside are these layers. It's a one-way capacitor. It's taking a big volume, amplifying it, and shoving it through in one way. That's what we want to do. So when we want to create these capacitors like this, that's basically a capacitor, but it's also a diode, because it doesn't create a big enough magnetic field in order to push it back to the original. So therefore it acts as a diode, but it also acts as capacitance. So when you get that normal coil in the center, it'll act like an AC flyback. Very, very little spark like this, right?
Right.
But when you put in the capacitance like this, now it grows like this, right?
Right.
But that's what we're trying to do in all this stuff. We want to capture, put it in there. We want to force it. That's what those things, one over the other, over the other, over the other. It forces it to create cavitation in there. Now we can get it to go a lot higher in voltage, right?
Right.
It's kind of the idea of all of it. If you want to get to some type of over unity or really high efficient unity, you know what I mean? That's where you have to start.
Well, you mentioned cavitation, and cavitation kind of has the idea that electrons or molecules are being picked off. And so let's use, I guess, water for an example. You'll put a positive and a negative voltage in the water, and it'll start to cavitate. It'll start to break the water bonds, the molecule bonds between oxygen and hydrogen. Is that the cavitation you're talking about? Is that an example?
So you're talking about structured water. It'll actually make a vein in the water and where it structures, right?
Yeah.
The energy we work with releases that structure. So if you're taking that structure and you're turning it off and on between both, that's what I'm talking about. Because the energy I use, it works like a gas. So as you turn it between on and off, it filters to the next layer naturally. You see what I'm saying? It's a pulse. It's a beat rate. It's going like the earth does. It's like the heart of the earth. You know what I mean? Going like this. And it lets it through, and then the next layer cavitates, and the next layer, and before you know it, because of the way the energy builds out, you have a bubble on the outside that's super thick.
Right.
So rotating a Tesla coil gets you a pretty thick bubble, right?
Right.
Not one you could see. But cavitating it first, that'll give you the one you could see.
So I'm very interested in this capacitor acting as a diode for high voltage. And you came to that conclusion when you took apart that flyback transformer.
Yeah, you could take a look at it.
On there.
Right. Yeah, there's no diode. It just has to be part of the construct that it's you said it's a coil, a capacitor, and a diode, the way it's constructed.
Yeah, the inside, just a coil. They put on a thick layer, so basically about as thick as a PVC pipe would be, a small one that would fit over it. And then they start rolling these things on top of it, which it basically, if you built the high voltage capacitor, this is exactly how you build it. You cut out the plastic sheets, you put your aluminum foil in there, and you layer it one by one, and then build it, right? Well, it's working on building the field out from it. So it acts like a one-way diode, because how much magnetic field do you think is on those?
I mean, you make a good point, because the magnetic field energy is stored is mentioned as henries. There's not going to be a lot of henries in that solid material. They're just not. So without not many henries, then it's not going to be able to create the magnetic field that was put into it. Right. It's not going to be able to recreate it. See that?
It can create an electric field, which is like a static field. So think about how your discharge comes out of there. It comes out more like a static field with very few amps, right?
Oh, yeah. It's a wider arc, which is a static. Electricity has a wider arc. It has that white color.
So there you go. It's just proving the point of how it works. You keep layering it, and then each one of them puts out more and more voltage, and it starts reducing the amperage because the heat can't penetrate that. It's going to stop at a certain level, and you need heat for amps, and you're not going to have a lot of it, so it's going to shoot voltage one way. It's going to act like your electric, but in voltage form. You know what I mean? As it passes through.
Right.
Super high electricity, very, very low amperage.
It makes sense. It's I'm really excited to test these theories that you have. In my head, it makes sense. I mean, to think of that something's an inductor and a capacitor, and it works in tandem with each other, though there's no capacitor. We saw that with my cone coil. If you remember in the last presentation, it had an
With
inch
the
thick
thick
of
bottom.
epoxy. Yeah, the thick bottom. And literally the only way it resonated is if I took all the capacitors away from it and it ran on its own capacitance. I think the technical term is what is it? Parasitic capacitance or self-capacitance. It was so large that you didn't need a capacitor. It was just all kind of built in. I'm going to hit my light. I'm in a dark room, actually. I'm going to get the lights here real quick. I am not on the surface of Mercury, though it looks like it. This is horrible. Oh, wait, you can kind of make out my face now. Oh, boy, sorry, guys.
Yeah, a little better.
It's my camera. It's horrifying. So questions in the comments.
By the way, everybody likes the fact that you have your camera on, Sean. They really do appreciate it.
It's a long road. I appreciate it, guys, your patience. Thank you. I have a health condition that makes it distracting sometimes, but I was feeling really good today, so I got my new laptop camera to look like this. But at least you have a face with the voice, so I appreciate it, guys. I hope to do it more, so thank you. Thank you. All right. Let's see here. We got a big crowd, 70, 76.
Yeah, there's a lot of people.
Awesome.
They like your presentation, Sean. You do really good.
Oh, thank you. I appreciate it. Oh, I built a pancake coil that I wanted to share as well. I had just too much in that presentation. I'm just impressed you guys can hang with me for an hour.
Oh, trust me, they'd stay longer to see pancake coils. They love pancake coils.
It's what was I able to do with it? Not much. But I'm on the right track. So I want to build a 10,000 winding pancake coil, and it only to be about like as big as a record. And so because I really think I can do some really fascinating things with such a dense pancake coil. And that's why I have that rectangular wire that I picked up from China, is because I can lay many layers and it be very small. All right, well, there's a lot of good discussions here in the chat. And
hey, Sean, I do have a question. You got that silver winding. What did you ever make anything out of that?
Thank you for asking. So I took an inventory of my projects in my lab, and I have 37 projects ongoing. And there I saw my silver wire languishing. I needed to print another sphere out of PLA because I only had one in nylon, and I wanted to have the same filament for the copper as well as the silver. That way it would be equal comparisons and to kind of see the advantage of silver or the disadvantage of silver. So that's what I was thinking. So I did pull it out. I brush some dust off of it, and I'm looking to wind the silver wire soon. The silver wire is expensive, so it makes me nervous too. The one good thing about pure silver wire is because of inflation, the price of silver goes up. So if something, if the world ends, I'll have 15 pounds of silver. Maybe buy me a loaf of bread in the apocalypse. So
Hey,
no, seriously.
think about it this way, though, Sean. You can always melt off the plastic and retrieve the silver.
And it's only always going up. So I might have paid something for it. But and the nice thing too about the Asian countries is they pay you by the weight of material. They don't in America you can buy a solid gold ring for $100, let's say, and then come back to the jeweler and they'll give you $10 for it. That's America. The other countries, you buy it for $100, and let's say gold goes up a little bit the next week. When you go to turn it back in, they give you the upper price. Let's say it goes up 10%. Nice. We don't do that here. We say it's used. nobody wants it. Yeah, well, but it's this much of gold. And so that's nice about having the silver. I'm kind of going overboard on that. So let's see here.
From what I understand, just so you know, Gerald says that the silver and the gold make a complete change in how the coil actually reacts.
Yeah, there's definitely something different in the makeup of silver, and we don't use silver in components. We use only copper or gold, and gold is only to plate things so they don't corrode. But silver tarnishes. Silver has its kind of own category, and I think it's the best conductor. I think it is.
Hmm.
I think it's the best conductor out of everything we're aware of. So yeah, I'm hoping to see something interesting. And Gerald's the pro, so I'll take his word for it.
It might just have to do how, everybody talks about electrons. It might be how to do with the amount that goes on there. You know what I mean?
Yeah. It's super efficient. It's not going to get the heat that would normally come in copper or other metals. So that's going to be interesting. It's not a superconductor, but it's going to have the more free flow of energy, if you will.
That's good. Less impedance. You got to love that.
Right. And it'll be interesting with such low impedance. I wonder how it's going to add to efficiency, because I dial these coils in so much that you're throwing high voltage with 2 or 3 volts in. And that means you're totally dialed in. And I wonder if silver is going to be next level. So I'm just perusing the comments here. Sorry, guys, I'm not reading them as fast as you're writing them. But Michael Merrick here talks about silver being a dielectric. That's interesting. It's anti-magnetic, he says, and he says it's antibacterial. I've heard this antibacterial about copper, but I've not heard of it about silver. But silver tarnishes, so maybe that tarnish is an antibacterial. That's fascinating. But dielectric, I'm not sure. I think everything has some dielectric property, but if you were to apply a voltage to silver, it's always going to conduct. It's not going to fight you. Dielectrics are something that'll fight you, where you'll start seeing the charges being pulled apart, and when you try to pull apart charges in silver, it just conducts. So it's an interesting point.
Gerald says I cannot pick up any ohms from my silver and gold coil. All zeros?
Crazy.
Yes. I told you it's different.
That is, I mean, you saw the cone coil and the cylinder coil that I shared from Ian, and his were 330 ohms each, and they were small. And you would think, well, copper conducts. It's not a 330 ohm resistor. No, copper has resistance. So to imagine that being significantly less, wow.
So let me ask you, if there's no dielectric to it, do the magnets just pass right by it?
Yeah, that's a really good question. In fact, I wanted to introduce magnetic fields to some of the plasma I'm working on. I don't know. That's a good question. Is the magnetic field around it going to be noticeably different? Is it going to handle plasma different?
I think it's going to handle a lot less magnetic field. The energy will be there, but if you tone down the dielectric, you're going to have less of a magnetic field. That's what makes it very, very important, because imagine wrapping your let's see what Gerald says real quick. No, I flush the magnets just like any other coil. It gets colder and it's crazy. Okay, hold on.
That is crazy.
No. If it gets colder and you're pulling in the environment, you're getting a lot closer to superconductivity. That's a big point.
That is, that's very interesting.
There you go. You just said it right there.
Yeah,
Hey,
it's
master of a coil. You know what I mean? You and him, it's like two guys in a room I'd love to sit in there with. You know what I mean?
you're so kind. I Gerald is always the guy you want to invite to a picnic. he's he's got some good stories, and I can listen to him all day. So yeah, so silver is been sitting in on my shelf for quite a bit, and it's 33 gauge magnet silver, 99.9% pure. I think I have 19 pounds, 15 pounds. I have a lot. And I have 33 gauge copper magnetic wire, and I printed identical cylinder coils, um, spherical coils, and I'm working on printing the conical coils. So they're all going to be in silver, and then a copper set.
Mm.
And so then that way I can say, here's copper sphere, here's silver, here's copper cylinder, and kind of do a compare and contrast.
That's really cool.
And do the, I'm sorry?
So that's a perfect way to do research right there.
Appreciate that. Thank you. So let's see here. John Bigman says, you were talking about the flavor of plasma. Plasma is one thing only, a dynamic spatial conductor. That's interesting. I know plasma's the most abundant matter in the universe. I've never heard of it worded that way. Dynamic spatial.
Well, but it has different properties, the different types of plasma you create. I can tell you that right now. You can't sit in a room with Sean's Tesla coil and not find that out.
That makes sense. Yeah.
If it avoids the crystal cylinder, right? But yet the next
Right.
one is attracted to it. Those are both plasma, but they're completely different properties.
Yeah. Yeah. It just, I mean, you saw me put the high voltage electricity through those spheres that I bought from China, and you saw that the plasma effects, the way they're ionized differently. You saw that green oxygen sort of turn into a wire. It looked like a wire. It was conducting. Yeah, so I think there's all kinds of different plasma. I agree with you. But as I say it a second time, a dynamic spatial conductor. So it's definitely dynamic because it's moving. It's spatial because it's flying off the tip of my Tesla coil, and air does become a conductor. So I guess that's an interesting way to put it. It makes sense.
Hmm.
Let's see here. Someone's the QUODTEN. Do you know how to say that,
No.
Nathan?
No.
Okay, so he says electrolysis is a really, 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 really good thing to learn for all. Yeah, I mean, you can make your own hydrogen. Let's see here. Creative Studio, super easy, just electrolysis with silver and distilled. Coat Creative Studio says, guys, my brain is exploding here. You guys are awesome. Way to go, Gerald. Let's see here. I'm slow. I'm behind here.
Oh, Gerald, the Coil Kitty experimental box coming analog. Nice. Joe did a video a while back. He had coils sitting out, and the cats came and sat on them. It was awesome.
That's awesome. Let's see here. So silver stands for antibacterial use. Think of vampires being killed by silver only. So, interesting point. Hey, thanks, Joe. Appreciate it. Oh, we got another Ian here. Excuse me.
Yeah, Ian pulled off, by the way, Ian
Mhm.
pulls off all of everything that we do. Like, he winds every coil. And it's very clean, very precise. He always
Yes.
takes all the perfect measurements off of them, by the way.
Yeah.
Yeah, he verifies everything that we do. So if you put it up, you better be ready to be checked because he's going to check it for you. That's for sure.
He does. He knows a lot, and he'll test your theories.
Oh, yeah.
Yeah, I think he's from Missouri, the Show Me State. No, he's actually from Ireland, I think.
Yeah, Ireland. I was thinking, man, Missouri, what?
Yeah,
I think he's
it
from,
was
I think he's in Florida, though. That's where I think
right.
he's at.
I think he works in Louisiana. I
I
think he
mean,
drives in Louisiana.
it's bog Irish. I mean,
Yeah,
you
I
know,
love his
tip your beer,
accent.
man. It's time to, you know what I mean?
Yeah, right, exactly. Thanks, guys. Too much kindness in the chat. Someone mentions here it's a Rugerstein. Colloidal silver is good for the skin, and it indeed will turn it bluish. Have you seen people ingest colloidal silver, Nathan, till they turn blue?
I'm not even going there, and we shouldn't either. That
Oh, that's right.
all medical would stay away from it.
Thank you so much for that. Yes, yes. Let's see here. The frill generator. It uses copper coil and a silver coil wound at right angles to each other. Don't know why silver coil in it. This is from LAN Lon. Interesting. I wouldn't think to put them at right angles of each other. I mean, that's food for thought. So there's so John Bigman mentions hydrogen plasma, nitrogen in the air plasma. Copper is a dielectric too. Have you heard of that, Nathan?
No, that I haven't heard.
Yeah, I haven't either.
What I'd like to see, Sean, is those cone coils. I know we don't want to see them like coned up like this to each other, right? But what I'd like to see is if you attach the wire together on the big ends of them and go down and taper from there, what it actually does. And it has to do with Otis T. Carr and how he had the center of that UFO device he had. It'd be interesting to see what he was actually looking at with that. And since you have the coils already and you could put a rod down the center, I think it'd be an interesting test to see what's up there. You know what I mean? Maybe put the main driving coil right in the center as like maybe 2 layers or something of the winding, and then just change the capacitors out as needed. But I think that would be an interesting test.
What was the name of the guy that you're getting the inspiration from?
Otis T. Carr.
Otis T. Carr. Because that's another thing. You guys are all well read in fringe science, and I'm only well read in the general physics. So I have to cross the barrier. Awesome. Yeah, will do. Since I have the cones, I'll let you know how it goes.
Yeah.
Thank you. All right, let's see. So for the occultism, which is not good stuff, silver is materialized moonlight. Okay. Ian asks, Gerald, how's Coil Kitty experimental box coming? Coil Kitty.
Yeah. I was just telling you earlier, he put out his coils, the kitty sat on them. But he's making a cool box. I'm kind of interested to see what Gerald's got going on there. He hasn't done too many more videos just yet, but
yeah. I keep seeing his cat whizzing on his router. That was my favorite.
yeah, he kept turning it off. That was funny.
I think it was a spilled glass from the cat, but the whizzing story sounds funner.
Oh.
So another guy, AKAEB
Ackaby?
Ackaby asks or mentions, did I see his comment about Darren Coulomb's conical coils, and get to check out his homecoming lectures about his coils in relation to Walter Russell's designs? Oh dear. I have a stack of good reading. I'll add that to my queue because it sounds fascinating. But no, I am fringe scientist illiterate. So but don't worry, I have a good mentor. Nathan's been awesome.
I'll send you a couple coil videos that are actually with the cone coil, so you can see what other people are doing. I think
Okay.
it'd be interesting.
I'll leave that then to reach out to you for that. Awesome. Appreciate it. I've been really interested in the coulombs because Coulomb is really, it doesn't talk about just about voltage or current, but it's volume. So I can have a real high pressure hose, but it could be as thin as a coffee straw. So it'll have low current. Or I could have a lot of current, like a fire hydrant. And that's just a lot of flow. I had a point here. Oh my goodness. And my brain just, boy, what was I saying?
Do you like the Coulomb?
Oh, coulombs, thank you. So Coulomb says, not only do you have a big electric field and you have a lot of charge, but you have a lot of current. You just have this sort of massive energy. And it was Jar Jar who was telling me or mentioned it to me that if we can get a Coulomb of charge, that would be jaw-dropping incredible. That would be breaking science. I mean, it's really hard to do. And so I was just really fascinated by that. And there's also a unit of measure, it's called a Weber. And so I'm going to be digging into coulombs and Webers because I think they're associated with different aspects of what we're trying to quantify. Thanks, Akabi. I enjoy your good comments and your chat and your support. It's great.
So hold on, a dielectric is high voltage stuck inside of a I don't want to say cavity inside of a material, right? But
so think of it as you have a piece of glass, a sheet, and one side of it is you have a positive voltage, and the other side you have a negative voltage, and the glass molecules get stretched. And that stretching means that they're going to hold that charge. If you disconnect the wires, they're going to stay with those atoms or those molecules being stretched like a rubber band.
I got it.
So, and then when you discharge it, you put a wire across each side of the glass. It then discharges out, and then the glass molecules come back to normal. Does that make sense? So it's distorts or orbits. It pulls electrons real hard here, pulls protons over here, but it doesn't conduct electricity because it's an insulator. And so that's that part of the capacitor that does not conduct. And then when you discharge across the plates, it allows it to discharge all that. So I don't know if that helps.
Well, yeah, but you just, I want to say this. A magnet is sticking the electric field, or excuse me, the voltage field and the magnetic field as one. Okay. So you can manipulate the current in that. But what you guys are creating is a high static field. So if you wanted to build both, you would have to be in two separate layers. One would have to be more of a magnet field, and then the other would have to be a pure electric, right? Am I wrong there? Because it sounds...
No, what you're describing is a magnetoelectric, which is part of Jarvis's patent application. And he mentions that. So you're taking So let's talk about a copper wire first. When you move electricity through a copper wire, it creates an electric field and a magnetic field. And so they call that electromagnetic radiation. But what Jarvis suggests is that you take a magnetic field not moving by itself, and you take an electric field not moving by itself, and you put them together, and instead of electret, it's a magnetoelectret. And so that's similar what you're describing is. It's not this electromagnetic radiation, but you're just basically taking these fields by themselves alone, not created by one or the other, and then you're putting them together. What's going to happen? That's one of the fascinating things about its magnetoelectric, because I can't find anybody who's done it, and I've researched it, and so it's going to be fascinating. It's not going to be easy to get there. Is that close to what you're talking about?
I think it is, but I don't know that you need to create the magnet part, because the magnets are already done. You just order them the way you want. I think the electric part is the part that you have to work on, and that's just my opinion. I could be completely wrong on the understanding of what you guys are doing, but that's just the way I see it.
What you're saying makes sense, because a permanent magnet is just a permanent magnet. But the thing is, how do you get that permanent magnet next to that permanent electret, and how do you layer them? I think that's what you're hinting to, and that's something that is in the research of Jarvis.
Okay, then there you go. That's probably what it is.
That makes sense. So let's see here. Akabe says Gerald has many different geometric coils. Oh yeah, he's the king of coils. I'm woefully behind him.
I think we all are. I don't think there's anything we could do to catch up yet. He's been doing it for 12 years, so he's got this whole system mastered.
It's a life's work for him. Exactly.
Let me tell you about my experience. I made a coil. Okay.
Okay.
Yeah, and I made my first one, and I didn't build the outside ring around it. Total failure. Okay, but at least I know the shapes that go into it, right?
Mm-hmm.
So, and even those may be wrong based on what shape you're looking for. So,
right.
I built another one, wound it. It took me longer to write out the numbers than it ever did to wind it. Winding it was basic. You could just flow one thing to the next, because I did a simple design.
Mm-hmm.
It literally took me 2 hours to write it down. It took me about 20 minutes to wrap the coil.
Wow.
It was like my mind mentally can handle wrapping the coil and understanding the next step. I hate looking at numbers to the side. I got to catch up all the time. You know what I mean?
Yeah.
And then because you're rotating it one each time, you have to change the numbers each time. And each time you rotate it, because it has to be 180 degrees out. So it's got to rotate in one direction, but then when you turn it on, it'll rotate the other, and then the other will rotate up. So how he keeps that straight in some of those coils that I've seen him build is just out of this world, man. You have to really do it for a long time.
Yeah, you know when you see a professional, let's say piano player, because they make it look easy. So Gerald in his videos makes it look easy, and then you go try to replicate it, and you're going, oh, okay, I cannot just in one day play the piano. This is something that's practiced, and if I don't get a kink in my brain when I watch his videos, I haven't watched them. I mean, he's on another level. It's awesome to watch.
Yeah, by the way, you'll never figure out his coils just by looking at them.
Probably not.
It's not possible. He has to tell you all the hidden secrets of it. I'm going to tell you that right now. And he has to tell you the parameters of everything before you do it. So, smart man. Very smart man.
Hopefully he'll write a book. I'd buy it.
He's got a big couple of them, little binders that he writes everything in and tests that he's done. So he definitely has a book on the horizon. You should publish it and make everybody cry with his knowledge.
Yeah, that'd be awesome. So 3D Havoc says, Sean, you might look forward to these presentations, but we all look forward to your presentation. Oh, that is so
That's right.
nice.
That's right.
That is so nice. I mean, guys, I'm on cloud 9. It means so much. I'm surprised, honestly, that you guys want to take part in this journey with me. It's awesome. So Gerald says he has one book to rule them all. Is that what he's saying?
He's written one book and waiting for editing on the second one. He's in progress of writing. That's
awesome.
Incredible. When are you going to publish it?
There's online publishers. Yeah, there's online editors. They'll take a cut, but it's worth it. So John Bigman says, be careful about going into the math. Sometimes they fudge the math to fit the theory. That's 100% right. My youngest daughter is a physicist, and she says, Dad, they lie with math. It's and if you talk to an honest physicist, they'll tell you they don't believe half of the physics they tell them. So yeah, good point, John.
Yeah, it'd be fun to sit in the room with a bunch of physicists, right? And just show them what we do, and then all the little parts and things of it, because it would really redefine how they see each part. So when they do the math, they know which one fits and which one doesn't. I think that would be amazing to see.
I totally agree. There's a he's the professor of physics and math at University of Wisconsin. He's a Berkeley physicist, so he's a big name. He adopted my daughter as his granddaughter, and he's very open-minded. He's not, I'll tell him some of my weird theories about gravity, and he'll just smile and he's like, go for it. And he knows a lot, but he's not afraid to look at things and be open-minded. So yeah, that's something I think to put on the list for later. There's some family things going on right now, but to show him some of our stuff. He's eloquent, he's kind, and he's crazy smart. And him to put a little bit of, this is what's going on that I think he could enlighten us because he's open-minded. He talks about PhDs who can't flip the switch on their computer to turn it on. And so he calls them worthless PhDs, and there's good PhDs. But yeah, I think that's a great idea.
I just think that, you know what, we need to go back to learning from each other.
Yeah.
And then we'll have it. That's it. That's all that needs to be done.
Yeah.
Because sometimes theories need to be redefined, and they have to see the physical proof that it needs to be redefined, and that's fair.
And having a new textbook come out every year proves that, because you can't grab a 100-year-old physics textbook and go, oh, look, I understand the formula for gravity. Nope. They've changed that quite a few times. In fact, there's a gravity constant that they changed it in 2017. So you're right about this. They don't have all the answers.
Chad says maybe you should come down in person. Hey, buddy, I'm planning a trip to your house, so I'm sleeping on your couch. So don't ever think I'm not coming. Okay.
And keep the cat that whizzes away.
Yeah. Not in no 30 degrees Celsius out there, whatever it is. No chance. But when it warms up, you know what I mean, where I can have some normal weather, I'm there.
I live in a cold climate here in the Chicago area, and you'll get days where you can take a cup of hot water and throw it in the air, and it freezes before it hits the ground. But see, that's in the middle of winter here. Where Gerald lives, that's what they call springtime, because he lives in the frozen north.
Oh, oh man, he's running around saying winter's coming, huh? That's bad.
Winter in Canada is no joke.
Oh wow.
No joke. All right. So Felix Audet makes the comment: electrics can be self-charging for some reasons, or can they be self-charging? I don't think they could be self-charging because they're like a permanent magnet. Can you magnetize a permanent magnet? No, it's already magnetized. That makes sense. Please excuse the gum. I don't have a health issue where my mouth is really dry, so I apologize if it's rude. Michael Merrick, math isn't science. I think math is the language of science, but math has been
Math is that's how you define it.
assumptions too. They go faulty assumptions.
No, I don't think it's that. I just don't think that they have all the information, and once they do, I think they'll define it the right way, and that's it.
Mm-hmm.
I mean, you can't work on stuff from the 1920s and expect to have everything figured out. There's got to be some new stuff, and I know they've revised and revised. But when you could show there's a total different phenomenon going on here, then you have to take account for it and then do the math on it. And I think you'd be all right. I love math, by the way. I love doing geometry. You know what I mean? I love figuring out exactly where things are, and I don't write it for anybody because it's not the kind of style of stuff that I do on my channel. You know what I mean?
Right.
I just put out the information so you have a basic understanding of it. I'm not trying to be the math channel. You know what I mean?
And you're a natural, so you make things accessible for people, and you are able to break it down, and you don't use the technical terms. And I think that makes this forum more open and makes people comfortable. You mentioned one time, you said you want to create a safe space for the flow of ideas. And I hate that word safe space because it seems to give the sense of victims, and we're not victims. But I think safe space is good in this, applying to this meaning where you really have just gotten people enthusiastic to share. You've gotten people enthusiastic to dig in and explore and experiment. I mean, I get messages from people who are saying they've tried to replicate what you've done, or they tried to replicate what I've done, and that's exciting.
Mm-hmm.
That's so exciting to me.
Well, what's cool is like if you need the STL file for whatever we got, we're glad to share it. That's kind of the cool thing, because then you're able to build it exactly the same. You know what I mean? As long as you do the same winding pattern, you're good to go.
Right.
You're not going to get any variance.
Yeah, that's true. It's true. My wife wants me to put up my still files for a small fee. I like sharing them. It's I guess a credit thing. If people don't give the right credit for using something of yours, I think that's when I think it crosses the line. So for example, when I created that ZBS for my circuit, Uber 1, Uber 2, and now Uber 3 I'm working on, I have credits at the bottom of the diagram. And it has 4 or 5 YouTube channels that are my inspiration, or I derived from, because I don't want to take away from anybody.
There you go.
And if I make a circuit for somebody, I don't charge them a profit because I'm using other people's ideas. I need to get their okay if I'm going to charge. So I always do things that cost. I love it anyway. I can't do a lot because of my health, but when I can. But those are, I think, important things. Give credit where credit's due, and don't be afraid to say something dumb. I mean, that's half of my presentations.
I think I'm guilty of saying dumb things myself quite a bit. It happens.
Yeah.
I mean, it's hard sometimes because when you're first figuring something out, you're kind of feeling out the process of what's going on, right? So you may get it
Right.
wrong the first couple times, and then you have to redefine what you're saying because someone will always bring in something that's understandable, that's an actual physics principle, and you go, well, okay, I can live with that. You know what I mean?
Right.
I do that all the time. And some people say, well, you're changing your mind. Not necessarily. I'm just redefining it. You know what I mean? Getting fine-tuned in what's going on.
You're growing. Yeah. I always say I lie in the right direction. So
But the thing is, I show you the experiment too, so you can always just turn off the volume and judge by it.
exactly. And there's more than one way to say something, and there are more facets than people want to admit. And when you were saying about scientists are very much followers these days. We don't have anybody really pushing the limits, reinventing things, and I feel like fringe science kind of needs to be that breakout and totally question everything. Einstein did that because for the history of the world, everybody believed time was a constant, and Einstein kind of throws you off with no, clocks move at different speeds, at different velocities, different mass, different areas. So time is this rubber band, if you will. And when he wrote his general relativity paper, 100 of the top most renowned scientists wrote a paper saying Einstein was wrong. And who do we remember now? Do we remember those 100 scientists 100 years from now? 100 years ago, I mean? Or do we
I only
only
remember one name.
Einstein? So it's the same thing. It's just, you know what? I don't buy it, or I'm an honest skeptic. And to be honest, I think we're all really like, are you sure? Does it really work that way? I think we're all kind of that way. Do you agree?
Yeah. We all question it quite a bit.
Mhm.
Because one of the most disappointing things is when you get to a theory on something, right? And then you see the experiment they worked up. And being an experimenter, doing what we do, it's kind of hard to look at it and say, how did you get that from that? It's like you did a lot of extra thinking that we didn't do. So you have to explain a lot more because what I'm seeing doesn't work. Like I see people talking about, cold energy, and I can see a spark gap in a tube. And I know exactly what it is as soon as I saw it. You know what I mean? But maybe it's the vacuum in the tube creating the energy, because that's not, cold fusion, that's for sure. But it may be a different phenomena. You know what I mean? I'm all okay with that.
But you built a 100 or 1,000 failing experiments along with several successful experiments. So when somebody tries to come in and do something and is not following the rules of reality, you can point it out right away. I see it with Tesla coils. I go, oh, they added way too many components there. I mean, just shovel out 3/4 of those components. I mean, I'm working with 10 components, 4 resistors, 2 diodes, 2 transistors or MOSFETs. Oh, and those 2 toroids. 10 components. And I'll tell you, the Tesla coils that I work on can run with the best of them. I see people who will put in 100 component circuit. It's got IC chips on it. And it puts out sparks this big, and they're like, oh, this is, and that's fine. And I don't want to put them down. It's just that when they draw conclusions and say, this is how the only way to do it, or this is the best way or the only way, that's when I kind of say, no. But I know what you're saying. I get a little, oh, they should have done it like this. Do you ever get that way?
Oh, yeah. Well, it's like telling me all these things that go into a Slayer exciter circuit. And I pull out my one little transistor.
Yeah.
And I'm going, buddy, you haven't got close to the power I got yet. You're willfully behind.
You're the Slayer what's the word? Whisperer. You're the Slayer whisperer. It still boggles my mind what you can do with the Slayer. I can't do it, and I build 100 of those, and I look at yours and they make me cry. What do you think of my idea though of using a relay instead of a transistor in the Slayer?
That's interesting. I think you're on the right track. Jarvis talks about this all the time. So
Yeah.
think about it this way: if we took a dynamo, or basically we just took a generator, and we had this massive potential coming out of it, right?
Mm-hmm.
But then, instead of making it an open core transformer, just connect it directly to your number 2 coil.
Okay.
Or maybe put a spark gap in between right there.
Okay.
But now all that energy is past the gap and it's in there. The wire winding itself will transform the energy from a lot of amps to a very high voltage, right?
Right.
So now think of it as anytime you manipulate that, you're not blowing any circuit at all. You can't. The energy is going to be forced to go somewhere. That's what Tesla was doing. He wasn't allowing the energy to pass back like it does in our MOSFETs or transistors. They just explode on us with the heat. See, now that rod down the center can be manipulated. Now I could put it down a certain amount, change the frequency, and hold it there, right?
Yeah.
Or I could put it down quite a bit and create such a buildup and then let it out immediately and it boom, right through it, right?
Yeah, because you're tuning it to the perfect resonance. Because it's a variable inductor is what you're doing. It's a variable coil.
So now it has a massive amount of power going on the outside, and you can't stop it. It's gonna go until it's done, and that's it. And that was the point. We're breaking equipment by not doing what Tesla did, and it's cool because it works for so many different things, cheap off the shelf, but a little bit of thought process in it and seeing what he did with that dynamo, it really makes a massive difference.
Yeah.
By the way, my Slayer exciter, when I hook it up to my Tesla coil, since I put that 3D print that makes that perfect winding, Sean, as soon as I hook that Slayer exciter in at about 12 volts, the room starts to heat up. Like all the metal in the room starts to literally start getting hot. Like it's cold, but it's hot to the touch. There's a massive amount of RF coming out of that thing. So I built my coils, and I built another coil based on to get those things in resonance to make that plasma. If I just sat down and built another secondary only, matched to that exact number at 200, I think it's 56 kilohertz, that thing is going to be a monster. So, and the whole trick is I need to spark gap it out because I do not think a diode can handle it. See, that's the best thing about the spark gap is it's a natural diode. It goes one way and stops it. So I think if I do that, I'll be able to pull that energy easy out of it. Then we can start to use it.
Yeah, it's something that describes your electrodes where your transistor's cool to touch or room temperature, and you're throwing some serious energy out of it. And that speaks to how well tuned and how well you build it. When I'm getting, in most of my tests with the ZVS circuit, the components aren't at all hot when I have it at their exact resonant frequency. And so I think it's that sweet spot that you get in, because I've tried building your Slayer. I blow MOSFETs all day long, transistors. So there's something that you're doing that is, I don't know, it's precision, experience.
A lot of people, when they first build it, they'll take a Slayer exciter circuit diagram and they'll run it on a hot side, and they'll blow the transistor before they even start. That's one of the first things that goes wrong. They ground it out instead of realizing there's no ground on that circuit. There's no ground wire unless you put in capacitors. There's no ground on that circuit. So it's a completely negative run circuit. And the resistor in there is only to set the oscillation rate. So, yeah, it's completely different. A lot of people blow them out before they even get started, but I've had a lot of people get success on it. And you have to follow the diagram completely. The negative has to go back to the power source and not the ground. Right. And that's the most massive difference because all your energy comes out of the negative side. It doesn't come out of the positive side. And so many people get back to me, oh my God, I'm trying to pull it to the positive, so I only get the light bulb that lights up maybe this far from the coil. And they're going, how did you get that distance? Well, because you're still thinking positive energy. PNP is negative energy. It's not positive. From the key, it tells you right on the label what it is. It's not an NPN. It's a PNP.
Right.
It's run in reverse. And you have to apply those things to it.
And it's literally a resistor, a transistor, and a coil. It's literally nothing. It's not, and you're lighting those 4-foot long fluorescent bulbs with it, and it's this little circuit. Yeah, that's dialed in, definitely. We got a lot of stuff in the comments. Let's see here. Some good conversations. So
who used a triode spark gap? This is one of the most interesting things. This comes up in experimenting, by the way.
Okay.
For those of us who play with spark gaps all the time or used to with hot energy, one thing I love to do is put the screwdriver in the middle of it. Like, hey, I don't have energy. It's crossing yet. I'm going to put a screwdriver in it, right?
Yeah.
Well, you got to realize that's like a three-way spark gap. You literally, when you put that screwdriver in there, have the ability to pull the energy right out of the screwdriver.
Interesting.
Yeah, it's literally the three-way spark gap. That's what I love to use. So it's cool because now you got to think about it this way. Your Tesla coil, when it has nothing attached to it and it's just a number 2 coil, it's bipolar at that point. So the spark's coming out of the top and the bottom of it.
Right.
And there's nothing in between. So the only way to pull it out is the screwdriver effect, right? You have to put the screwdriver through the spark, and then you can pull it out. But then now you can capacitate without changing the actual value of that coil. You see, as soon as you put a capacitor to it, you change the value. That's no longer resonating. It's the same frequency. So spark it. Get the frequency of it, set your driving coil to it. Boom, you're perfect.
Is it like a kickstart?
You could see it as a kickstart, but it's like the reverse of the way you would normally use it. Normally, you just put it in there for a kickstart, yes. But because it still has the value of both of the energies into it at this point, combining the energies, you're going to be able to pull it out in a higher volume.
It's I'm trying to multitask here. Forgive me.
It's all right.
No, you're saying good stuff, and the guys in the comments are just really giving you some good feedback.
Yeah, they're smart. We got a great comment section, man, in the chat. They really know what they're doing too.
I know, so many good things. I can't keep up, to be honest. I know you and I are both looking at them, right, and talking. Let's see. So Ian Jackson mentions the Don Smith motor. You heard of that?
Don Smith, absolutely. I don't know if it's a motor, but a coil. Don Smith coil, absolutely. So I was watching a YouTuber today, and he had a ground rod. It was just copper. They put 2 Tesla coils over it. Now, it would get more energy on one side versus the other, right? And it had to do with where the wires of the Tesla coil are coming out. But in a Don Smith type, you would take that copper ground and you make it bigger. So just put it, I don't know what you call it, an adjustment size on it, and make the rod bigger, and then place your Tesla coil over it where there's very little gap. Now you get the most energy possible out of it, right?
Wow.
So, yeah, that's kind of Don Smith. So his is basically run on frequency too. So it's like a radio frequency, quarters, halves, you know what I mean, 3/4 waves, stuff like that.
Yeah,
Which
so you get more
follows
efficiency.
the musical scale. And as soon as you follow that and you have resonance and you create it perfectly, the energy comes out of the resonance. That's the whole key to it. Because
Yeah.
turning on a Tesla coil that has no number one winding on it is pure resonance, and you're getting plasma. So how do you think Don Smith did it? Multiple coils with multiple abilities to pull the energy into it, just like your ground. Remember? You're
Yeah.
using that big spool. He was doing the same thing.
Oh, interesting. Okay. Is he something you can Google? Somebody you can Google?
Oh, yeah, absolutely. He's everywhere on the internet as far as his design. Just put in his name, and it'll pop up with a bunch of different things.
Don Smith Coil, as I Google?
Just put in Don Smith, and it'll come up with a bunch of things. Or, yeah, you can put in the Don Smith coil. Yeah.
Awesome.
You'll see
Have
it.
you heard of, what's that?
Let's say once you see it, you'll understand.
Sounds good. I'm taking notes here, so I'm not ignoring you. So someone mentions the grav inductor. Have you heard of that?
Graviducer? I know there's people out there that are working on a like a UFO machine, and it's called I think the Graviducer.
Oh, this has a T, so it grav inductor. It
No,
might
I
have been
haven't.
inducer.
No, I haven't heard it then. Might be the same thing. I'm reading it wrong.
No worries. Let's see. Ian Jackson says he used electromagnets that were paramagnetic dielectrics made from PTFE and silver wire. I think PTFE is Teflon. Paramagnetic dielectric. I'm not getting that.
Okay.
Sounds interesting.
The paramagnetic is interesting because it hides the magnetic field. It is the same thing we're doing with the one wire energy. That's why the bismuth is so important, because it's the same type of thing. It's doing the same thing. By the way, just as a heads up, Joel Legacy or Legance, one of the best people out there for Don Smith right now. He's going through, yeah. He goes through different books and reads the parts that are coming out and what they do, and then he builds a circuit based on those. He's built a lot of cool things on there on the radio frequency end of it, and how to build a ground to it to make the coil winding work. That was really cool. He's also done peg cell. He's been on here, and he's presented as well. Joel's a really good guy.
What's his name again?
Joel Legance is what I would say, but most people just know it as Joel Legacy.
Because I saw that presentation. I actually subscribed to his YouTube channel, so I appreciate the reminder, because I did like what he presented. So I'm very interested.
Okay, here we are. Graviductor. I didn't say it right. There you go. Probably thinking of the same one. Non-momentum warp drive. That's cool.
Yeah, that bends the mind, but you can't say it's wrong, but it sounds doable. It's very cool. All right, let's see. There's a discussion about occultism. Interesting.
PTFE is Teflon.
Yeah, that's what I thought. I know I bought some to make electrodes because Teflon is very positively charged, or no, is it very negatively charged? It has one of them extremely charged.
I like to run something out of stainless, to be very honest with you. I just want to, yeah, I want to see the properties of it.
Like wire or
more of a like a thin casing, but with holes all over it. And I want to see how the amount of electricity absorbs into it or is bounced off of it. You know what I mean?
Yeah.
And if it has any properties like eddy current in it, which I doubt it does, since it is steel after all, it'd probably pull them in, but it may have a variance because it's stainless.
Yeah.
I think it's very interesting. I just want to try a little piece, you know what I mean? See what's going on with it, what it does. Sometimes the strangest things you try have the most amplification for some things.
Right. They make stainless steel flour sifters. And they're made out of stainless steel, and they're basically a cage. You're supposed to put flour in and sift it, but is that kind of what you're looking for? That's something you can just put over.
Is it like a spaghetti thing?
It has super tiny holes, like smaller than your screen door or your screen and your windows.
Right.
And it's a half a sphere, and it's stainless steel, and flour goes through it. And flour only can go through it.
Okay.
And it's stainless steel. And
I hear what you're saying. It's like the aluminum screen material. It's so small.
And it's stainless steel, and you can put it over something.
So let me ask you something. Here's something for your kitchen. The one you use for spaghetti, is that stainless steel? Or is that just coated steel?
You can get stainless steel. We have a stainless steel one.
Because that would be the half sphere that's the same one I'm looking for with the same amount of holes, you know what I mean? Kind of a big one. It
doesn't have a lot of holes, though, if that makes sense. Do you want a lot of holes?
Yeah.
Then you want to get the sieve or the sifter.
Okay.
Yeah. If you Google sifter, stainless steel sifter, and it's funny how you ask it, we are always on the same wavelength. I was Googling a sifter literally this morning, and now you're asking for one. And I wanted a stainless steel one. Yeah. We are on the same wavelength.
You gotta be, Sean. We work on the same stuff, you know what I mean?
Yeah. I've worked with a lot of people, and I've not been on the same wavelength with any of them. I think you've really brought a group of like-minded people together, and that's special. And you can see it in your subscribers. I'm just looking at my iPad because it shows you broke 7,000. That's so awesome. And I think the sky's the limit with your channel. You're putting in the hard work, and people love it. It's just awesome.
Yeah, but we're gonna have a couple more of the inventors that are usually in the chat. We're gonna start looking at their work, Sean. I got 2 of them lined up, so they'll be able to come on. Awesome. And it's absolutely fantastic, the stuff that they're doing. So, you know what I mean? We all push each other. So, yeah, I mean, show what you got, and we'll all take a look at it, and you get some people who've done a lot of inventions, and then we'll all be able to help each other get to the next level. Think of something that somebody else didn't. Yeah. That's kind of the point of the whole show, isn't it?
Right. Yeah, exactly. Not easy to do, though. You can look at the Fringe Science channels, and kudos to them, but they're not really attracting. What's the word? I guess it's a sense of community. I think that's what you're really spearheading, is a sense of community, where like-minded people can have the free flow of ideas. When you look at other Fringe Science, it's kind of more about a guy and his experiments. But your channel's more, hey, I'm doing experiments, but what are you doing?
Yeah.
And how does that fit with what he's doing? And that, I mean, just kudos to you, Nathan.
Oh, well, thank you. And we try to make it the best environment possible, Sean. And then I love it when people present and show what they do. It really makes everything come together, because it's like we're the engineers, right? It's basically what it comes down to. Is we're basically a bunch of engineers. So we're the guys that kind of keep to ourselves a little bit. You know what I mean? Kind of work on stuff. Love when things work out. But we're kind of the guys you want to sit around and have a beer with in the campfire. You know what I mean? Because it's always the most interesting conversation, because every story that comes out is like a real life experience where we got shocked one day, or, something started lighting up across the room and you weren't expecting it. You know what I mean? Just all the cool stuff.
It's awesome. Well, it's coming up on 7:30 Chicago time, my friend.
About that time.
Yeah, and it is that time. I had a blast. The smile from sharing on your channel lasts for at least a week until the next week. But I want to appreciate you guys in the chat for your active listening and your support and your good ideas. I want to thank you, Nathan, again for this amazing channel and letting me present. So I guess with that, I'll sign out.
Right on, man. Thank you very much for coming on, Sean. I really do appreciate it.
Thank you. Appreciate it.
Everybody in the chat, man, thank you very much for hanging out with us today. We do appreciate it. And everybody, have yourself a great night.
Much love. God bless.